Okay, let's pick up from where we were. So the next big chapter is wave in optics, and it includes 4 subtopics here, which is general wave properties, of course, reflection and refraction, interference and diffraction of light, and lenses and mirrors. Again, let's go briefly through each. So general wave properties. So first of all, you should know the relationship between speed of propagation, wavelength, and frequency. And remember, the speed of propagation can change only if you change the medium, and the frequency can change only if you change the source. So the speed of propagation through the string is given by this square root of a force of tension divided by, this is called the linear density, so mass over the length of the string. And here are some frequencies of the standing waves for nth harmonic. And this is the bit frequency, just the absolute value of the difference between the frequencies. Okay, so let's look at this question. This is a fairly simple question. So it says light wave traveling at light speed has a frequency of 6 times 15 times 10 to the power 15 hertz. So what is the wavelength? Well, this is straightforward. You use this formula and you plug the numbers in, and okay, the answer is A. So this is fairly simple. So let's look at other example here, reflection, refraction. So first of all, you should know the definition of the index of refraction. It's how many times slower light travels in a given medium. So this is the law of reflection here, and this is the law of refraction, also known as Snell's law. Okay, so the question gives us this figure. And it says the light striking the surface of the piece of the glass from the air and the refracted beam are perpendicular to each other. What is the index of refraction of the glass? So first of all, if these two are perpendicular, well, we know of course from law of reflection that this must be 35 as well, and if the whole thing here is 90, then this angle here is 55. Right, so but you gotta remember that the angle of incidence or angle of reflection or angle of refraction measured not from the interface but from the normal to the interface. So this is your angle of incidence, and this here is the angle of refraction. So now, applying Snell's law, you should get this relationship, and because we're talking about glass and air, so the index of refraction for air is 1, so that's why, and 2 is just equal to sine 55 over sine 35, which is option D here, and we're done. Okay, you just have to know Snell's law. Okay, so another example about lens and mirrors. So first of all, few equations. This is the definition of the strengths, optical strengths of the, or optical power of the lens, and plus or minus here indicates that it's positive for convergent lens and negative for divergent. Okay, so this is a thin lens formula. It's distance between the object and the lens, this is distance between the image and the lens, and this is the focal length. And remember that this could be negative if the image is virtual, and this is the magnification. It's just the distance over distance to the image over distance to the object. So if we read the question now, it says object is placed 20 centimeters from divergent lens. If the distance between the lens is and the image is 8 centimeters, what is the magnification? Well, okay, so you're basically given the distance of the image and distance of the object, so You apply it directly and you should get 2/5. So the reason I used -8 here, because we're given that this is the divergent length. And for divergent length, you should know that the image will be virtual. So that's why we treat di as -8. And so that gives you option B here. Okay, so let's go to the next question. Okay, so this is about interference and diffraction slide. So relevant equations. Of course, here is the condition of the maximum for double slit interference, and this will be the same for diffraction as well. So what you should understand from this equation is that the optical path length difference should be the multiple of the wavelengths of the source in order to have the constructive interference, which is a bright fringe. And condition for minimum, it should be the optical path length difference should be proportional to half of the wavelength, so that will correspond to distracting interference. And here is the equation that helps you to determine the position of the fringe for mth order. So where d is distance to the screen and little d is the separation between slits. Okay, so let's look at the question, and it says consider double slit interference experiment using yellow light of a wavelength lambda with slits labeled S1 and S2, and if P is the center of the dark fringe on the screen, on which the resultant diffraction pattern is projected, which of the following equations relating S1P and S2P, the distances from slits respectively to point P, could be true? Well, again, if it says that this was the dark fringe, it means we have the minimum, and so we just have to see which of the equations satisfy the condition of minimum. And we can see that all of those are multiples of lambda, including option E, because that corresponds to m equals 0. So there is no difference. However, we're looking for minimum condition, so that's lambda over 2. So that tells us that it should be option A. Okay, so let's go to next question, next section, I mean. This is heat and thermodynamics. So here we have several subtopics. It's specific and latent heats, thermal expansion, laws of thermodynamics, and heat engine efficiency. Okay, let's look at all of them separately. For specific and latent heats, you don't need to know a lot. You just need to know this formula for heating something up without changing its state of matter, and this is actually about changing state of matter. So this could be any latent heat when you change water to vapor or ice to water. Remember, if you're going from gas to liquid or from liquid to solid, this becomes negative because you actually have to take the heat away. Okay, so let's read this sample question carefully. It says a block of aluminum and a block of iron each absorb the same amount of heat, and both blocks remain solid. So the mass of the aluminum block is twice the mass of the iron block. If the specific heat of aluminum is twice as the specific heat of iron, then... Okay, so you basically have to look at this formula here. We're given that, okay, the mass of the aluminum block is twice as large as iron, and the specific heat is twice as large as iron. So then the increase of temperature should be smaller, right? Because the aluminum requires more heat per kilogram. The aluminum requires more heat per degree per kilogram, and so since it's more massive, so the temperature change should be smaller because they both absorb the same amount of heat. And so that corresponds to option E. The increase in temperature of the iron block is 4 times the increase in temperature of the aluminum block. Okay, so let's look at the next question. Thermal expansion. So relevant equations here are fairly straightforward. So if you have linear expansion, then it's just new length over initial length is proportional to change in temperature, and alpha is the coefficient of linear expansion. And if you're talking about area, it's just exactly the same, except you multiply it by a factor of 2, because if you think about it, it's two-dimensional object, so it expands in 2 dimensions, and for volume, it's 3-dimensional object, so it expands in 3 dimensions. Okay, given this, we should be able to answer this fairly easy question. It says, which of the following equations best states the relationship between the material's coefficient of volume expansion due to heating and the coefficient of linear expansion? And well, that's what we just said. So the coefficient of volume expansion should be just 3 times greater than the linear expansion, which is option B. Okay, so let's go to the next section, which is laws of thermodynamics. So for relevant equations, I put something really basic too, such as definition of pressure. It's force per unit area, because this is something to keep in mind. Okay, this is your ideal gas law. Of course, you should know this in your sleep. And this here is... So this here is the first law of thermodynamics. Change in internal energy is input heat minus work done. This is one of the ways to formulate the second law of thermodynamics. The entropy always increases or remains the same. And this is, recall from chemistry, this is the molarity equals to mass over molar mass, or number of particles over Avogadro's number. Okay, so sample question here is, what happens to the pressure P of the ideal gas if the temperature is decreased by a factor of 2 and the volume is increased by a factor of 8? Okay, so obviously you should use this ideal gas equation here, and if you rearrange it a bit just by dividing both sides by volume, you get this for initial pressure, and for pressure after this processes, you should get this. We just substitute 2T instead of T and 8V instead of V, and if you simplify it, you get this. So that means that the pressure decreases by a factor of 4, which is option B here. Okay, again, as I said, if you know the equations, that shouldn't be very simple. It should be very hard. Okay, heat engine efficiency. Well, for this section, you literally need to know the definition of heat engine efficiency, which is work done divided by input heat, or it could be, the work done could be expressed by input minus heat loss, which is denoted as heat sink. Okay, and so it says, during each cycle, the heat engine with efficiency 25% takes 800 joules of energy. So how much waste heat is expelled during each cycle? Well, you apply this equation here and you figure out that the work done is 200 joules only. So that means, like, if it took 800 and output only 200, then it means we just lost 600. So that's option E here. Okay, so let's look at our next section. That's modern physics. So for modern physics, we have several subtopics. It's general quantum phenomena, atomic models, nuclear and particle physics, and special relativity. Okay, so let's go over each of those. So quantum phenomena. So first of all, you should know that energy of the wave is given by frequency times Planck's constant. Those equations are photoelectric effect equations. So this is maximum kinetic energy, and this is initial energy minus the photon minus the work function of the metal, and this is the de Broglie wavelengths of any particle. And here is known as red threshold for photo effect. So you need some minimum frequency, which corresponds to maximum wavelengths, in order for photoelectric effect phenomenon to occur. So if the frequency is smaller than work function divided by Planck's constant, then the photoelectric effect does not occur. And that is exactly what the question is asking about. So it says, in the experiment designed to study photoelectric effect, it is observed that the low intensity visible light of 550 nanometers produce no photoelectrons. And it says, which of the following best describes what would occur if the intensity of this light were increased dramatically? And well, if you think about it, it's all about frequency, it's not about the intensity. So intensity means we make it brighter, but it doesn't change the frequency, so you should right away answer that nothing will happen. Okay, let's look at the other question. So for atomic models, I just put this little equation here, that is to say that the energy is quantized, so it can occupy the electron in an atom can occupy only certain energy levels. And well, you need to know about Bohr's model and Rutherford's model and the gold foil experiment. Okay, so the question gives us this energy diagram, and it says, well, which of the following gives the energy of the photon that could not be emitted by this atom? Well, so you should rely on this formula here. So basically we say energy is quantized, and of course energy must be conserved, so you should scan through these options and see which number cannot be produced by subtracting any pair of those two, of those numbers here. So if you look at it, we have a bunch of ways to emit the photon, and so if you scan through, you will see that 42 doesn't appear in here, 302, 255, 64, and 17, they all appear, but 42 is not right because it should be 47. So this means that a photon cannot have energy of 42 electron volts. Alright, let's proceed to the next question. So nuclear and particle physics, I would say relevant equations here are just the radioactive decay equation, and you should know three types of decay: alpha, beta, and gamma. So you should know that in alpha you emit helium nucleus, beta decay means you emit electron and antineutrino, and gamma just emits gamma quant, so there is no change in mass number or charge number. Okay, so the sample question gives us this reaction with a known particle X, and it says identify particle X. So what we should know here, that mass and charge both must conserve. So this gives us two simple equations. Simply, okay, this mass number plus mass number equals to this mass number plus mass number of this unknown, which is denoted by A, and similar for charge. And if you solve those simple equations, you should get mass 1, charge 0, and I hope you know that this must be a neutron. Okay, let's look at the special relativity questions. So first of all, of course, you should know Einstein equation for energy mass equivalence. And here are three equations for length contraction, time dilation, and relativistic mass by L0, T0, and M0. I denote the mass in I denote this quantities in non-moving reference frame, and here is the relativistic quantities. And also, please remember that speed of light is c in any reference frame. This is one of the postulates based on which Einstein came up with his special relativity. So please don't forget this, because many questions are actually trying to trick you, hoping that you will not remember this thing. Okay, so let's look at this question here. It says 5 identical spaceships take off from planet X. Each passes by planet Y at a constant speed on its way to planet Z. Science station planet Y observes them passing by. The spaceship traveling at which of the following speeds would be observed to have the greatest length? Okay, so, well, you get a look at this equation here, and well, it looks like it's very straightforward. So it should be, the smaller the speed is here, the larger the length becomes. So you just have to compare those numbers and pick the smallest one, and that's it. Okay, so we're almost there. We just want to talk about this miscellaneous thing. So for miscellaneous questions, it means it could be any general knowledge about evolution of stars, universe, important discoveries in physics, results of major experiment, or any general analytical skills. So being able to apply physics in real life situations and something like that. So this section shouldn't take more than 10% of the test, and typically it's 4 or 5%, which is like 3-4 questions on the test. And the example of such question is given here. It says, which provide the basis of the observation that the universe is expanding. And again, probably it's not very straightforward to answer this question. But if you think about it, well, the zeroth laws of thermodynamics probably is not a very good option here, because it just tells us about thermal equilibrium. So I don't think it's relevant here. But again, as we said at the beginning, if you have absolutely no idea what it is, probably leave it blank. But if you can eliminate at least one option, you should go for educated guess. So the answer here, if you're curious, would be answer B, because redshift is it's basically a Doppler effect. So the wavelength of a receding source increases, and if we're talking about light, it becomes sort of more red if you increase the wavelength. So that's why it's called a redshift. So the redshift was observed for every galaxy that we can see from Earth, and that means that it is a receding source, which means they're going away from us, and that tells us that the whole universe is expands. So that's why this is the evidence of universe expanding. Okay, so that should give you a very good idea of SAT test and what to expect from it. And as I said, the questions are not very hard. You should just practice, and then when you come to the test, you should already know how to do the questions. If you have enough practice, and if you're focused, you have a good attention, you should succeed. And I'll stop here. Good luck.